Hello and welcome to Brunei Math Club. In this video, we study invertible matrices and inverse matrices. Okay, let's start. So far, we have been studying matrix addition and matrix multiplication, and you may be wondering, what about matrix division? For real numbers, say if A is a real number and if A is not zero, then we always have A inverse, which is 1 over A, such that A times A inverse is equal to 1. And of course, A inverse times A is equal to 1. In the case of matrices, we only consider square matrices if we want to deal with division or inverse matrix. So A is, say, n by n matrix. It's a square matrix. And if there exists some x, which is of again n by n matrix, such that Ax is equal to Xa is equal to the identity matrix, then this x is called the inverse matrix of A. So x is the inverse of A. And we can show that such an x is unique so that x is written as A inverse. And if the inverse of A exists, then we say A is invertible. Or we say A is a regular matrix. Let's see a few examples. Consider this matrix A, 2, 4, 3, 5. Is this matrix invertible or does it have the inverse? Let's find out based on this definition. Okay, so let's say its inverse. Suppose the inverse exists and its inverse is written as x, y, z, w, for example. Then according to the definition, Ax equals to Xa equals to the identity matrix. So first let's calculate Ax. Ax is equal to 2, 4, 3, 5, xy, zw, which is equal to 2x plus 4z and 2y plus 4w and 3x plus 5z and 3y plus 5w. This is equal to, this should be equal to 1, 0, 0, 1. Since these two matrices, this and this, are equal, we should have 2x plus 4z equals to 1, and 3x plus 5z equals to 0. So this is a set of simultaneous equations for x and z. And we also have this. So 2y plus 4w is equal to 0. 3y plus 5w is equal to 1. So let's solve them. For this one, we have, let's see, let's multiply this by 3, so we get 6x plus 4 times 3 is 12, z plus 3. Multiply this second one by 2, we get 6x plus 10z equals to 0. Let's subtract both sides. We have 2z equals to 3. So z is equal to 3 over 2. And from this one, x is equal to negative 5z over 3. So negative 5 over 3, 3 over 2. That's negative 5 over 2. And from this one, let's see. From this one, we get y plus 2w equals to 0. So y is equal to negative 2w. Let's substitute this into here, we get negative 6w plus 5w equals to 1. So w is equal to negative 1 and y is equal to positive 2. Therefore, x should be equal to, x is negative 5 over 2, y is 2, z is 3 over 2, and wait a minute, 3 over 2, yeah, 3 over 2, and w is negative 1. This matrix X was obtained from the equation AX equals to the identity. But does it really satisfy XA equals to the identity? Let's check it out. So negative 5 over 2 to 3 over 2, negative 1 times 2, 4, 3, 5. So this is, this times this is negative 5, this times this is positive 6, and that's negative 10 plus 10, and that's 3 minus 3, and this is 6 minus 5. So this is indeed the identity matrix. So this matrix A is invertible, and its inverse is this. And here's another example. Let's say matrix B is 6, 4, 9, 6. Is this invertible and has a inverse matrix? Let's check it out. Again, let's say if its inverse exists, then let's say it's x made of x, y, z, w. So calculate this. 6, 4, 9, 6, x, y, z, w, which is 6x plus 4z and 6y plus 4w, 9x plus 6z, and 9y plus 6w. This should be equal to 1, 0, 0, 1. So we have the equations 6x plus 4z equals to 1 and 9x plus 6z equals to 0, and also 6y plus 4w equals to 0, 9y plus 6w equals to 1. Okay, let's take these equations first. Okay, so let's first divide both sides of the first equation by 2. So we have 3x plus 2z equals to 1 over 2. And divide the second equation by 3, then we have 3x plus 2z equals to 0. But look, both of these left-hand sides are the same, but the right-hand sides are different. So these equations cannot have solutions. Therefore, the inverse matrix does not exist. And you can check this similar thing for this part. So this matrix B is not invertible, and the inverse matrix does not exist. Okay, next let's study some basic properties of inverse matrices. Suppose A is an invertible matrix, and let's say we have two inverses of A. So that means AX is equal to AXA is equal to the identity, and AY is equal to YA is equal to the identity. Then X must be equal to Y. Let's show this. So X is equal to Xi. I is the identity matrix, of course. Multiplying by the identity that doesn't change X, so we have this equality. But using, let's say, this equation, the identity matrix is equal to A times Y. But matrix multiplication is associative, so we have XA times Y. But XA is equal to the identity matrix. Therefore, we have this, but IY is equal to Y. Therefore, X is equal to Y. So, if the inverse matrix exists for a given matrix, then the inverse is unique. For this reason, given a matrix A, its inverse is written as A inverse. So it's a unique notation given the matrix A. So to summarize, if the inverse exists, then we have A times A inverse is equal to A inverse times A is equal to the identity. And next property, suppose A and B are both invertible, or regular, if you prefer, then AB is invertible. And its inverse, so AB inverse is given as B inverse times A inverse. Showing this is pretty easy. So we just multiply AB by this thing, B inverse A inverse. Using the associativity of matrix multiplication, we have A times B inverse and A inverse. But this one is the identity matrix. So this is A inverse. But this doesn't change anything, so this is A times A inverse, but this is equal to the identity matrix. And similarly, B inverse A inverse times AB is equal to B inverse times A inverse times A times B. And this is again the identity matrix. And B, and this is equal to B inverse B. This is equal to the identity matrix. Therefore, the inverse of AB is equal to B inverse times A inverse. Then we are done. And next property, if A is invertible, then A inverse is also invertible. And its inverse, so A inverse is equal to A. So the original matrix. Okay, let's show this. This looks pretty obvious, but showing this can be a little bit confusing. But anyway, let's do it. In order to avoid the confusion, let's put x equals to A inverse and y equal to A. And calculate AXY, which is A inverse, because we're just multiplying inverse with A, so it's the identity matrix. And YX is equal to A inverse, which is of course the identity matrix. Therefore, X inverse is Y, which is A, but X is A inverse. So inverse is the original matrix, and we are done. And finally, let's try to find the general inverse for a 2 by 2 matrix. So let's say A is A, B, C, D. And let's say its inverse, if it exists, X, P, Q, R, S. We don't write A inverse at this point because this might not exist depending on the values of A, B, C, D. So anyway, so based on the first definition, A times X is equal to X times A is equal to I should hold, right? So let's calculate AX first. So that's A, B, C, D, P, Q, R, S. That is A, P plus B, R, and A, Q plus B, S, and C, P plus D, R, and C, Q plus D, S. And this should be equal to 1, 0, 0, 1. Let's write this down as a set of simultaneous linear equations. So first, from the first one element, we have AP plus BR is equal to 1. From one element, CP plus DR equals to 0. From 1 to element, AQ plus BS equals to 0. CQ plus DS equals to 1. And let's solve this one first. So first, let's multiply the first one by D. Let's say, name it 1, 2. So 1 times D, we have ADP plus BDR equals to D. And 2 times B, we have BCP plus BDR equals to 0. So we have the same term here. So subtracting both sides, we have AD minus BCP. So this one here is equal to D. So if AD minus BC is not equal to 0, then P is equal to D over AD minus BC. And similarly, let's multiply 1 by C, and we get ACP plus BCR equals to C. And 2 times A, we have ACP plus ADR equals to 0. And subtracting both sides, same term here. So we have BC minus ADR is equal to C. So dividing. So again, if this AD minus BC is non-zero, then we have R equals to minus C over AD minus BC. And what about the remaining equations? Let's say this is 3 and this is 4. And again, 3 times D minus 4 times B. We get AD minus BCQ equals to minus B. So again, if AD minus BC is non-zero, then we have Q equals to negative B over AD minus BC. And similarly, multiplying 3 by A, not A, C, minus 4 times A, we get BC minus ADS equals to minus A. So again, if this holds, then S is equal to A over AD minus BC. So for all the cases, if AD minus BC is non-zero, then we have, to summarize, P is equal to D over AD minus BC, and Q is minus B over AD minus BC, and R is minus C over AD minus BC, and S is equal to A over AD minus BC. But what happens if AD minus BC is equal to 0? Then from this equation, if this is 0, then B is 0, right? And from this equation, if this is 0, then A is 0. And from this equation, if this is 0, then D is 0. And from this equation, if this is 0, then C is 0. So A, B, C, D are all 0. Then that means A, B, C, D are all 0. But this is a contradiction. We are not assuming this. So in this case, A is not invertible. Therefore, its inverse doesn't exist. So you can see that this quantity AD minus BC, when the matrix 2 by 2 matrix is given as A, B, C, D, then this quantity AD minus BC is an important quantity to determine whether the matrix is invertible or not. And this quantity is called determinant. And in later lectures, we will study the properties of determinant for general square matrices. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.